Hello everyone. For the research seminar presentation, I'm going to do a presentation on the paper titled Photorealistic Single Image Super Resolution using a Generative Adversarial Network. This research was done by a group of 11 scientists at Twitter, and this was published in November 2017 in the IEEE Conference on Computer Vision and Pattern Recognition. As of now, this paper has been cited 4,278 times, and you can access the paper by visiting the given links. So let me get started explaining what we mean by super resolution. Super resolution in simple terms mean given an image of low resolution, we are going to increase its resolution by a certain factor, preferably keeping the image details intact as much as possible. So the applications of this image super resolution are huge because it can vary from satellite imaging, where we need to improve the resolution of the satellite so that we can view on the details. There are applications in improving the quality of media content, medical imaging. There are use cases in face recognition, surveillance, and lots of other fields as well. Let me also explain the terminology that we come across in this paper. There's something called SRRGAN. GANs are very popular field of research in the current world. GAN refers to a generative adversarial network, and here SRRGAN refers to a GAN designed for image resolution, image super resolution. There's something called SRResNet as well. SRResNet basically refers to a deep residual convolution neutral network which is optimized for referring to the peak signal to noise ratio, which is designed for image super resolutions. Now here you might also come across the concept of perceptual loss, where perceptual loss is a loss function designed based on the content loss calculated in a VGG feature space, as well as an adversarial loss, which is a discriminative function which compares the super resolution image to the ground truth or the natural image. There's also something called the MOS testing, where MOS means mean opinion score, where the opinion of a group of individuals are considered and the mean is taken, and the aim of this MOS testing is to overcome the limitations of the MSE based quality measures, which is the mean square error based quality measures. Let's also clarify the problem statement at hand. What we basically need to do is, given a low resolution image, we need to obtain the high resolution image corresponding to that. In mathematical terms, what we need is a generative function g, as you can see in the equation, which will return the high resolution image given the low resolution image. Here theta g is a parameterized representation of g, and our aim is to solve this equation that which you can see on the screen, where the LSR represents the perceptual loss function, and we apply this equation to all the images from 1 to n, and by solving this equation we try to find a solution for the solution, and hence the generative function g, where, as I explained earlier, here theta g represents the weights and biases of the function g, and after solving this we'll be able to find the generative function, which will provide us with the capability of improving the resolution in order to obtain a higher resolution image given the lower resolution image. So in order to make you better understand what they have done, what they have provided through this research, and to explain you why the earlier methods fail, let me first take you through an example. So what you see on your right hand side is the original image, and on the left hand side is a 4x downsize image, and we are going to increase the image on left by a factor of 4 so that we can get the image on right side. So let's see what we can do with this image. And something very simple that we can do is to apply a fixed upscaling filter such as the bicubic interpolation filter. But as you can see, the results are not that good. The image is still blurred and we can't figure out which is which. So that's not a really successful filter. Now let's try something else as well. And here what you can see on left is the SRResNet filter, and here we can see the quality has been improved by a substantial amount, but still the image looks a bit artificial and the perceptual quality is not that good. And the reason, which I'll be explaining in detail later, is that the function that we use here, the loss function, is a MSE loss, where the mean value of the pixel-wise mean value is considered, which results in losing of the finer texture details. So this is the point that this research has been trying to address, and they have been successful in addressing this via the SRGAN. So let's see what happens with the SRGAN. And as you can see, they have almost made an image identical to the original image by using the SRGAN and a perceptual loss function. So we'll go into details in the next slide. As I explained in the previous slide, what has motivated the research team to perform this research is that the MSC based optimizations has their limitations because it encourages average like solutions, and as you can see on the graph from on the left, the image surrounded by blue color, it shows the MSC based optimization, which is a pixel-wise average of all the possible solutions, and that is not really good. It does not represent any of the separate images in total. That's a mean obtained by collecting all those images and having their pixel-wise mean. So it's overly smooth and generally loses all the features when we apply it. However, as you can see by the yellow box, the GAN actually generates a much better perceptually accurate representation when we consider all the other images. So when we apply it using a VGG feature loss, where VGG is also another architecture of neural networks. So there are different VGG networks such as VGG16, VGG19, VGG54, and this research team has tested with all those VGGs, and what they have selected for this SRGAN is VGG54. I will come into the details later. So here what happens in this VGG feature loss is, instead of selecting a pixel wise average, they go for a higher average where a feature space average of possible solutions is selected. So instead of overly smoothing by considering the pixels, they consider a feature space and take the average of that feature space. Now let me explain about the perceptual loss function that they have used. The perceptual loss function comprises of two components. One is the content loss and other one is the adversarial loss. Content loss of the perceptual loss function ensures that the contents, the features of the images are not lost, and the adversarial loss component is there to make sure that the image looks real. So this content loss function could have two possible values, that one is we can either take a MSE based content loss function, and or we can take a VGG feature based loss function. What they have used in the SRGAN is a VGG based loss function for this content loss. And when it comes to the adversarial loss functions, which is that determine the image looks real, what actually happens there is there's a discriminator. So discriminator again is a GAN. So it checks whether the image of which the resolution was improved has any difference with the ground truth or the real image. So the basic function of this discriminator is to check whether an image is real or fake. So what happens through this adversarial function that you can see in the equation below also is that we trick this discriminator into thinking that SR image, a super resolution image, is real. So that the super resolution image looks convincing enough to be a real image. So when it comes to the solution architecture for the generative function or the generative network, they have used a relatively deep neural network, and which comprises of B residual blocks, which has been bypassed by a skip connection. And for the image upscaling in the final section, as you can see, they have used a sub-pixel convolution. And when we talk about the discriminant function, the discriminant network, that is also not much different from a VGG architecture. They have done minor tweaks, like they have introduced a leak relief activation, and they have used stride convolution instead of the max pooling, which is usually there in VGG neural networks. In this research, they have also experimented on the impact of the number of B residual blocks on the performance. And as you can see in the graph, as the number of the residual blocks increases, the performance has been always seemed to increase. And for this scope of this paper, they have stick to the number of blocks 16, which they identified to be a perfect balance between the number of blocks and the amount of residual blocks, which optimizes the computational complexity. And they have also found that the skip block has to support an increase in performance, as evident in the graph. So in general, the network depth has been contributing positive for the performance, and it's also has been identified to be beneficial for the peak signal to noise ratio. However, the SR gain gets more difficult to train for deeper networks. So through their investigations on content loss, they have tested with the VGG features here, and I explained to you this earlier as well. They have tested with the VGG 22 and VGG 54. Here the number usually refers to the number of layers in the neural network, and as you can see, as the number of the layers increase, the performance has been notably improved, as you can see in this table. As I explained to you in the initial slides, they have also performed a mean opinion score, and this was done with 226 human raters, and they have been asked to rate these images from 1 to 5, where 1 represents the worst and 5 represents the best. And as you can see through this diagram, the SR GAN has received rating which is almost identical to the original HR image. It is a rating which is higher than any of the other methods, which you can see the bicubic interpolation or the SRCNN or the SRResNet. SRGAN has surpassed all these features compared to the existing features in the earlier research. So what I have included in this slide is a visual example which shows how much better the SRGAN performs to the earlier methods. So the SRResNet, which you can see in the first image, fails to produce the finer details of the image. SRGAN, however, with a mean square error, also is not that much successful in producing the fine texture details, as the MSE loses or over smoothens the features by taking an average of the pixel values. Now, SRGAN with the VGG neural networks has produced substantially good features. So as you can see in the third picture, and you can also see as the VGG number increases, as the number of layer increases, the quality of the image, or the perceptual quality of the images increases. So this VGG 54 and SRGAN, this is the result that they present through this paper as the SRGAN. So obviously you can see that the result they produce through this SRGAN is much more convincing and closer to the original real image. What you can see here is, instead of 4x upscaling, they have gone for 16x upscaling after training the model on the Celib A. And as you can see, you get astounding results out of the SRGAN. However, here SRResNet is also not that bad. However, if you consider SRResNet with SRGAN, you can see that SRGAN has been able to produce much realistic, more sharp features overall. So here is another example, and something special about this is, although the image quality is better in the SRGAN, which is the lower right hand corner image, than all the other images, there's something special about this, because you can see, if you look closely, that SRGAN fails to reproduce text much clearly. The number 96 is not that much better in the SRGAN image. However, this is because this image has been trained on ImageNet, and ImageNet specifically does not have any textual or other implementation, just images. However, if it was trained for textual images, we could have obtained better results. So the training data is something really important in any neural network, and especially in GAN and SRGAN as well. What they present as the conclusion of this is, the SRGAN method they have presented is able to produce more photorealistic images than the state-of-the-art reference method. And in general, the training data is something really important in any model, especially GANs, and they look forward for improved techniques to train GANs, and they are also interested in finding good objective functions which is better able to capture the perceptual quality of an image. That was a brief introduction into the single image super resolution with SRGAN. And if you have any questions or any clarifications need to be made, please feel free to reach out to me. Thank you.